TechRabbit here again. Now we're going to dive into Rust expressions. So let's say hello to Rust expressions, and in Rust expressions can return values. So let's have a look at some examples. We'll have a look at a expression that returns a numerical value. So here we define result, and then we say that we have the first value and the second value, and then we make a sum of that using the Rust convention, and the last line is evaluated as the return value without actually using a return statement. So not really used to that syntax. So you can actually replace this first value, second value with a number 1 and it will still work. So it's like, yeah, so whatever's on the last line in an expression, then that gets evaluated as the return value and gets assigned to result. This is also interesting that an if expression can be used to initialize a variable. So for example, here we say let is okay, and we're checking a result, and then you return true or false. And a match expression can be passed as an argument to a function or macro. So as we see here, you have the println macro, and then we have a placeholder for the value, and then we actually, as the value, we directly use a match statement. So it calls this function called positive number, and then it returns a result of either true or false, and then we return a string true or false. Now what Rust doesn't have is that if you're been working with C, C++ and stuff, then you have this ternary syntax, and this is not supported in Rust, so you can't write this type of syntax in Rust. And then when we're talking about these statement blocks, when you have blocks, then so you can use a block wherever you need a value. So that's kind of like you can now we can take some examples here. So for example, false, you can just have it as a statement block, expression block, and then that can in itself contain a function, and then it will just return the result of this this value or this procedure expression block as the result. And the way this works is that, okay, so if it's true, then it just returns a true, and then if it's false, then it does this extra evaluation, and then returns the evaluation, is it negative or not. So of course counterintuitive. Just thought I'd make this example. Let's see. Going down here. I'm trying to keep these examples to really show the core message about the feature of Rust, but with trying to keep the examples as simple as possible. You can make they can use more complicated syntax and more complicated structures, but I think that kind of misses the point. So one wants to really just focus on what's the main meaning behind different this feature sets in Rust. And this is actually a kind of a useful function that Rust prohibits match expressions that do not cover all possible values. So here we're looking at, is it positive, and then true will return true, and then if it's false, and false. But if you comment out this last statement here, then you get a error which says that it's a non-exhaustive pattern, and that can be useful when you're actually defining other than booleans, where you have different types of enumeration types. Then it will actually warn you that, hey, you're missing, you're not handling all the cases. So And then all blocks of an if expression must produce values of the same type. So here we see here. So this one here, positive sign, if positive number is true, false. But then if we see here that if we suddenly, and this is actually I think very good, because not specifically in this syntax, but in when you're programming in C and stuff, that then you used interchangeably, or used the constants true and false mixed up with, you know, the numeric value representing true and false, which can be, depending on what type of implementation you're looking at, you can use the language standard definitions for true or false in a numeric form, or something else. So, because of course as a programmer you can actually create your own definitions of what numeric value true is and what is it false, so you can create parallel definitions. And in Rust you can't do this. So you can't mix definitions, like in this simple case where you have positive sign, and then it says that if it's positive number, then is it true, but then you say, okay, the false would be 0, but then it would say up. No, you can't do that. So, and then we have one more form of if, which is the if-let expression. So this is more like for pattern matching. So if we create an option, some value, and we say that it's sum 42, and then we want to compare it to an actual option that has turned up, so we say that, okay, the y value is 42, and then we could do a comparison if let sum y is some value. And then we have a slightly different example with a different type. So we say today is Monday, and if let Monday is day, and then we said it's the starting of the working week. It's not Monday. And then this might actually make more sense. Like I added the more theoretical description. So an if-let expression is shorthand for a match with just one pattern. So this shows it in its more like pure form. So max expression with, you know, the pattern matching, and then you have block 1, and then you have basically all other options is block 2. So that's a kind of, as you see, a little bit more shorthand way of handling it. And we move on to looping, and there's 4 looping expressions. So we have the while condition, and then we loop, and then while let, pop, and then I added I tried to find the simplest, most descriptive example of how for example for while let. So this is like pop values from the stack. So we define a stack, and then we take the top value. So we say sum, the collection of sum, and then we say the top part of it, and then we do a pop on it, and then we get the actual value. And then iterate over a string, so we have a bunch of chars, and then we iterate through the characters. So C getting the value of each character, one after the other, and we loop through those. So that's the while let. And then we have the standard. We have the simplest, which is just a loop, and then it loops until it hits a break. And then the for pattern in collection, so a bunch of numbers, and then it's just iterating through the reference of the numbers, and prints out the whole list. So that's the for with patterns. And then the loop expression itself only returns an empty value. The condition must produce a type bool, so you can't make any other looping conditions. It doesn't evaluate to a Boolean. And then you have the option that you can actually define ranges that you loop over, and this is like those that have worked on Python and stuff to fill in that. So you say, okay, so let's print a range between 0 and 20. But then one has to take into account that it's open-ended on one end, so then it only loops to 19. So that one of the most common mistakes I tend to make is that I always forget this. It's open-ended, but on one side. And then we see. And then for loop over a value consumes it. So if you don't use a reference, then it'll eat up the values. And this we've covered in a previous video. And basically you end up in a trouble where if you try and then if you haven't used the reference and then you try and use the strings, then it'll crash. And then of course you have a reference to mutable collection with not. And then the Rust break only works in loop statements. And then a continue expression jumps to the next loop iteration. Pretty standard stuff. And then, so let's have a look at this. A loop can be labeled a lifetime. So here, for example, we put on the outer loop, we've labeled it as search. Then it will go through this loop again, and then if it finds the letter B, then it will exit. It will break to search, which means that it will exit to the external loop. So break will exit for string loop. Labels can also be used with continue. Then we did some return expressions that are fully covered. We already did that in an earlier session. Here we have a little bit of a more tricky code coverage. There's a kind of code coverage analysis in Rust that it tries to go through the different code paths and identify if there's a dead condition, so that code will never be executed. Now you can go and look at this. We can actually go have a look at that. Let's see. It was here. So here's a very simple loop that has been defined, and this is again with Rust. The problem is that depending on what compiler you run and what documentation you read, that structure or that pattern shouldn't work. Shouldn't compile, but it actually does. So with the compiler version that I'm using, it actually does compile. And yeah, it's sad to say this is Rust. not totally used to this, that you get these major shifts in how the compiler will treat different things. That if you read some documentation of certain patterns that work, or it can go both ways, sadly, in my experience, that some patterns that are documented to work will suddenly not work, and then it will be the other way around also, that patterns that shouldn't work, they do. So yeah. And then we have a divergent function, and basically this is a function that kind of loops forever, or a loop that loops forever function. So here, and the way you define a loop forever is that it never returns. So you actually define it in the function declaration that this function will never return. So this can be used, for example, to start up loops for message queue monitoring, or forwarding messages, or monitoring a port, or more like system styles. And this function never returns, indicated by type. So it's actually a type. And then here we have function and method calls. Maybe not, are types of expressions, one can say. So here we define a sum, and then this is the like function call syntax, and then it's the issue. Okay, what does a static method call like? So this is actually using the Rust style class player, and actually we are actually going to come to that in a later episode. But I actually did add an example of a Rust, how you define a class in Rust. It's a little bit different from what we are used to. But as I said, I'll come back to that in more depth later. And then if you want to make a method call on the class, then we have a class instance, then this is the syntax. And the dot operator makes an automatic dereference of values. Then there was a syntactical thing with the return statement, which I actually thought I'd add here. Might be confusing. So syntax is in Rust thinks less of is less than is intended. So you can actually uncomment this, then you'll see the error that it produces. So it actually, when you have it in this syntax coming up to that one, then it will, the parser will get like, what do you mean? What do you mean? What is that? And it's not that obvious to what's the problem. If you write this, then you might initially think that what's the problem with this syntax. But anyway, the way it should be written is that you should separate out the type definition, so that it's clearly easier. Let's say you make it unambiguous for the parser to know exactly what the heck you're meaning. And then it's also the recommendation. Of course, you should try and avoid defining type definitions where they're not needed. So if the compiler can infer the type, then you shouldn't use them. Sometimes a bit tricky. And then we have some fields and elements. So like player name, accessing a struct field. So if we actually go up here, alright, no, we need to look at the class definition here. So here I have a simple, as part of the class definition for player, then you have the struct player, and then you see you have the name there. And then you can access the instance of that. Nothing really amazing. And then there's the a tuple example, so that when you're accessing tuple entities, then you can use this dot index format. So this actually accesses the tuple value 2, also partially actually covered in previous videos. Square brackets, access to elements array, slice or vector. So I added a few simple examples here. Access an element using an index, so quite simple there. And then extracting a slice from array or vector. So here we take a slice of numbers, say from 1 to 3, and then access the element using an index from the slice. And then the value left of the brackets automatically dereference. And then here I put in a little bit extra, so with this kind of ranging, so when you want to have a range, then what is the syntax like? So that's the full range, and then you give a start index and then an end index, and then between two. And then this Rust range of half open, they include the start value if any, but not the end value. And I tend to always get that wrong. Only ranges that include a start value are iteratable, and this handling this becomes with experience. So you just write code, and then stuff that doesn't work, you adjust it. So because the compiler infers when it has a start value, like if you're starting the slice from the beginning, or it's not super clear when it infers that it doesn't have a start value. And then array slicing supports 4 forms to introducing a default start value. Let's see. The unary operator is used to access the value pointed to by the reference. I tried to make a simple example here. And then we have x is 5 and y is reference to x. And that is assigned to y. So then you actually go here and you tell with star that you want to actually go get the actual value. This is probably used mostly in more low-level code, in my experience with Rust, so you don't see it that often. And then also a few notable comments about the arithmetic bitwise, comparisons and logical operators. This is the integer overflow is detected in debug builds and causes a panic. So, and this might be interesting. So if you're always compiling your code as released, then you might not catch issues you have in your code. You can run unchecked arithmetic if you use certain library functions. Like there's a bunch of them, but here's like a wrapping add. So you can use. There are other functions. And then check divide by 0 returns the option. Something I made wrong here. No, I think I was going to write and there. And then unary negates the number except the unsigned integers. Bitwise not uses that. Bit shifting is always sign extended on signed integer types and 0 extended on unsigned integer types. Bitwise operate a higher procedure than comparisons. And then when we're comparing two values, they have to have the same type. With these functions, the types need to it needs because these are specific for booleans. And then this is actually was a notable that I decided to include was these increment and decrement operators are not supported, and this actually gets you when you're just into code writing, and then you're used to using plus plus minus minus, and then you can't, and then you write a bunch of lines, and then you no, I can't use it. I forgot that. Rust has typecasting options, and then you actually do specific conversions. Numbers may be cast to any of the built-in numerical types to any other, and then it can be converted to integer types. Some casts involving unsafe pointers types are allowed. And this can actually catch you that some type implementations, the deref trait. So if you have a type that implements internal dereferencing, then it may, in the syntax of your code, do the typecasting for a certain type of operation automatically, and that you actually have to just look at the documentation for details. And then the last detail is that we have a lightweight function like values. So is even, and then you can define. This is kind of like a macro, lightweight function like values. I don't know if that's the right. That's what they used in the literature, but I think this is semi-equivalent to macros. Shorthand. Precedence and associativity, that I recommend. There's lots of tables in the documentation that says, okay, well, what comes before what, and sometimes I think that's better to look up in the tables in the documentation. So that was Rust expressions. I hope this helps. And as per convention, I'm going to upload this to my GitHub site, so you can actually download this this whole project and play with it yourself. And it's also meant to be like a quick lookup list for anything related to expressions. So hope you find it useful, and happy hacking.